Hello and welcome to the latest C2GLearn webinar from the Carnegie Climate Governance Initiative. I'm Nick Harrison, and for those of you not familiar with C2G, we're a time-limited foundation-funded initiative of the Carnegie Council for Ethics and International Affairs, and C2G's mission is to catalyze the governance of climate-altering approaches, in particular for large-scale carbon dioxide removal and solar radiation modification. And to find out more about these topics, you can visit our website at www.c2g2.net and scroll down the page to click on the C2GLearn button to watch further episodes. Now, today we're going to learn about how the Working Group 3 contribution of the Intergovernmental Panel on Climate Change's sixth assessment addresses large-scale carbon dioxide removal and solar radiation modification, and explore what, if any, implications this has for governance. Now, the new report, published in April 2022, is the third of the three working group contributions to the sixth assessment, and you can find on C2G's website further briefings and other C2G learns covering the first and second working group contributions too. Now, at almost 3,000 pages in the main report alone, there's a lot to take in, but fear not, for to help us on our learning journey today, we have three experts who were among the 278 authors of the report, who will help us to understand how CDR and SRM is covered. So let me introduce you to our speakers who join us live today from Norway, Thailand and Japan. If our speakers would like to switch their videos on, here we are, welcome, great. First up is Glenn Peters. Welcome, Glenn. Glenn's the Research Director and Senior Researcher at CICERO, which is the Centre for International Climate Research in Norway. And he was a lead author for Chapter 3 on mitigation pathways compatible with long-term goals. So welcome to you, Glenn. Thanks for joining us. And second, Joashri Roy, who's the inaugural Bangabandhu Chair and Professor at the Asian Institute of Technology, Thailand. And Joashri was coordinating lead author for Chapter 5 on demand services and social aspects of mitigation. And welcome, Joashri. Thanks for joining us. And thirdly, Massa Sugiyama, who's Associate Professor at the Institute for Future Initiatives at the University of Tokyo in Japan. And Massa was lead author for Chapter 12 on cross-sectoral perspectives. And welcome, Massa. Thanks for joining us. Now, we'll begin today with presentations from each of our speakers, followed by a Q&A session where the audience can send in questions and we can elicit some answers from our three experts here. So to begin with, we'll have Glenn take us through the emissions scenarios consistent with 1.5 degrees with a focus on CDR. And then Joashri will tell us a bit more about how CDR is addressed. And then Massa will tell us a bit more about how SRM is addressed in the report. So the presentations are pre-recorded, so you can watch them again visiting the webpage after this event. So I'd like to ask my colleagues now to go ahead and play the presentations. Thank you.
Hello, everybody. Great to join you. Today, I'm going to talk about emission scenarios consistent with 1.5 degrees of global warming, and I'm going to focus on carbon dioxide removal. And the scenarios I'm going to use are based on the IPCC 6th assessment report, the Working Group 3 part of that report, which was published around about a month ago. So first of all, I'm going to go straight to showing a few scenarios and talking through those. So this figure here shows global CO2 emissions in a set of 1.5 degree scenarios, those that have no or limited overshoot. I'll mention what that means in a minute. On the vertical axis here, we have global CO2 emissions, and on the horizontal axis, we have time. The black here is emissions that have already occurred, historical emissions. So there's about 100 scenarios in this figure, and they all have generally the same characteristics. There's a peak in emissions, which needs to happen pretty much immediately, as soon as possible. After that, there's a rapid decline in emissions, and they reach net zero CO2 emissions around about 2050. You will see here that some scenarios reach net zero CO2 emissions a little bit earlier, some a little bit later. Then after they reach net zero CO2 emissions, they go net negative. So on a net basis, carbon is being removed from the atmosphere overall. This is a 1.5 degree scenario with what's called no or limited overshoot. So this means that the scenario the temperature in the scenario increases, gets to around about 1.5 degrees or maybe up to 1.6 degrees, and then comes back down below 1.5 degrees. And these negative emissions after net zero, they're helping bring that temperature back down. There are other scenarios which have 1.5 degrees with high overshoot. They might go up to, let's say, 1.5 degrees before coming back down. They probably, in most cases, require a little bit more carbon dioxide removal. And you can also look at, for example, 2 degree scenarios. The 2 degree scenario would look very similar to these scenarios here, but the net zero year would be shifted to, let's say, around about 2070, meaning the rapid decline in emissions after the peak is slightly lower, still quite rapid. So this is the sort of global picture looking at aggregated total CO2 emissions. In the next figure here, I want to pull that apart a little bit. This is a figure that's coming from the IPCC assessment report in a box on carbon dioxide removal. It's showing total greenhouse gas emissions. We've taken the vertical axis off here, so there's no numbers, so it could represent a country, if you like, not just the global emissions. And I call this figure the anatomy of scenario. We're trying to show the key components in the scenario and how that works. So if you look at the top part of the figure, the brown, grey and the orange, these are deforestation in brown, fossil CO2 emissions in orange, and in grey, and in orange, non-CO2 emissions, things like methane and nitrous oxide. In a 1.5 degree scenario, generally you'll see they all go down quite rapidly, but they don't reach zero. So in the middle of the figure and towards the end of the figure, you see in particular fossil CO2 emissions continue, as do non-CO2 emissions. And this is essentially why we use or see a lot of carbon dioxide removal in these scenarios. So the green at the bottom here is carbon dioxide removal. We've put some emphasis here on the dark green, which is removals coming from managed land. Could also be coming from afforestation, but also forests that are just standing there taking up carbon. This is already seen in many countries' emission inventories, and we've tried to emphasize that today we already have some level of carbon dioxide removal. The light green out towards the second half of the century there's other types of carbon dioxide removal, those that we don't really have much of today, such as bioenergy with carbon capture and storage, direct air capture, soil carbon, and so on. So now, as I mentioned, the CO2 emissions and the non-CO2 emissions don't quite get to zero in these scenarios, even though they decline rapidly. And therefore, carbon dioxide removal is used to offset those emissions that don't go to zero. So why can't we get emissions to zero? You could think about, maybe long distance transportation still has some emissions. Chemical production might still have some emissions, steel production might still have some emissions, or they might be very costly to reduce emissions, in which case it is seen in the model at least that it's cheaper to emit and then remove that carbon back out of the atmosphere with a different technology, carbon dioxide removal. In the agriculture sector, where you have methane and nitrous oxide, it's very hard to decarbonize those, probably can't get those emissions to zero, and you might use a level of carbon dioxide removal to help offset those emissions. Moving out to the second part of the century here, from 2050 onwards, or after net zero, you'll see all these scenarios here, or this illustrative scenario here, I should say, goes net negative. So the black line and the black dotted line both go below zero. So carbon is being removed from the atmosphere, and that brings temperature back down from a peak, as I mentioned in the previous slide. So the main interest here today is on the carbon dioxide removal. So I'm going to talk a little bit more about the bottom half of this figure, the green parts. How big is that part of the figure? So this figure here shows carbon dioxide removal in those scenarios that I showed in the first slide, 100 or so scenarios consistent with 1.5 degrees with no or low overshoot. And the numbers here are quite large. There are some challenges in estimating these emissions. I'll talk about that on the next slide because of different definitions with different variables and different types of carbon dioxide removal. But the scales here are large. So to put some perspective on the scale here, if you take a, let's say a coal power plant and assume that it's using biomass and with carbon capture and storage, so a bioenergy with carbon capture and storage facility, or you take a rather large direct air capture facility, one that we have not remotely seen around the world, but let's say takes up about 1 million tonnes per year. So I'm taking here 1 million tonnes per year removal at a facility as sort of an average large scale facility. Then you would have to build one of those every week out to 2050, and you would get to 1.5 billion tonnes per year. That's much lower than the median here in this figure, which is 5 billion tonnes a year. So to get to 5 billion tonnes a year, you're talking about building several of these large scale facilities each week out to 2050. So these numbers here are immense. Moving a little bit more into the different technologies here. So this figure has 4 different types of carbon dioxide removal: bioenergy with carbon capture and storage. So you grow biomass, that removes carbon, then you burn the biomass for energy, but catch the CO2 and put it back in the atmosphere. That's bioenergy with carbon capture and storage. Direct air capture is a machine essentially, which essentially sucks carbon directly out of the atmosphere, and again, you store it. Afforestation, growing forests, and enhanced weathering, using rocks to help take up some more carbon. So you'll see clearly in this figure, most scenarios use bioenergy with carbon capture and storage. Just about all scenarios report this a variable, and it's used at scale. Direct air capture, only about 1/3 of scenarios use that technology. It's relatively new technology, so there's much more uncertainty about its deployment levels. And also, if you use more of that technology, it might displace some of the bioenergy with carbon capture and storage. Afforestation, this one's a little bit more challenging because most models, and actually all models, report net land use change, and net land use change includes afforestation, but only some models, about 2/3, record this afforestation variable directly. So we don't have a good handle on the size of this removals from afforestation in total. And you'll see it starts at 0 in all these scenarios here, whereas the previous figure I was talking about, afforestation and managed forests, already exist today. So there's a sort of a baseline issue. So we need to be a little bit cautious of the carbon dioxide removal in the afforestation. Then enhanced weathering is shown on the bottom right there. Not many scenarios include that technology at all. But this gives you a sort of idea of the different technologies and how they're included in the scenarios. So just wrapping up, scenarios use large-scale carbon dioxide removal. I would argue, some will disagree with me, but I would argue that the scale is implausible given the real-world developments. Now, I expect that we would have some level of carbon dioxide removal. The question is really how much. Some level of carbon dioxide removal is likely to be beneficial. As I sort of mentioned, maybe carbon dioxide removal is the cheapest option in some sectors that are hard to mitigate, let's say chemical manufacturer, and maybe we need it to offset, let's say, fertilizer use, so nitrous oxide emissions in agriculture and so on. And an important point here is that carbon dioxide removal only really has a function if emissions are actually being mitigated. There are no real scenarios where emissions can continue as normal, and then we just use carbon dioxide removal to bring those down. We could simply never get carbon dioxide removal at that scale. So carbon dioxide removal only makes sense if emissions are also being reduced drastically. And I'll finish up there. Thank you for your attention.
To share with you the major messages coming out of Working Group 3 on governance of CDR. Let me share my screen. The major message is that unless there are immediate and deep emissions reductions across all sectors, 1.5 degrees Celsius is beyond reach. And accelerated climate action is critical to sustainable development. The evidence is clear, the time for action is now, and there are options available now in every sector that can at least halve emission by 2030. Early strengthening of mitigation actions in this decade reduces substantially CDR requirement until 2100. This was also a major conclusion from special report on 1.5 degrees Celsius, which is P1 pathway, which shows how low demand scenarios reduces the CDR requirement compared to high emission scenarios. The faster we reduce emission in the next decade or so, the less we will need to rely on CDR to achieve and sustain net zero, or to reverse warming that we have already caused. Any further delay in climate policy substantially increases carbon lock-in and mitigation challenges. It creates dependence on carbon dioxide removal technologies for meeting the Paris climate goals. For the first time, IPCC report has discussed CDR methods substantially in chapter 12 and has also devoted one full chapter on demand side mitigation actions. Chapter 5 of IPCC Working Group 3 report shows in the demand side at a global scale, there is untapped mitigation potential to bring down global emission by between 40 to 70% by 2050, starting immediately by scaling up policies, providing access to infrastructure and end-use technologies that are already tested, tried, and have proven effective. Table 5.2 in chapter summarizes long-term scenarios that aim to minimize service level energy and resource demand from assessment of this emerging body of literature, that low demand scenarios can reduce both supply side capacity addition and the need for carbon capture and removal technologies to reach emission targets. Historically, most long-term mitigation scenarios have taken technology-centric approaches with heavy reliance on supply-side solutions. And the use of carbon dioxide removal, particularly in 1.5 degrees Celsius scenarios. Comparatively less attention has been paid to deep mitigation side reductions, both in long-term integrated assessment models and energy system demand models. The three high confidence statements need to be read together from this Working Group 3 report, which sends out a clear message. Large-scale deployment of CDR may not prove as effective as expected, as depending on the type of CDR used and likely to negatively impact food availability, biodiversity, employment, water stress, energy affordability and access, and mineral resource extraction, suggesting it may not be a viable carbon removal strategy in the next 10 to 20 years. Also, large-scale deployment implies heavy reliance on CDR methods, most of which have not been implemented at scale yet, which is also presented in table 12.6 of the full report about the technology readiness of the different CDR methods. However, lower energy demand achieved through behavioral change or the infrastructure use or provision of different end-use energy technology can reduce emissions, and the requirement for CDR will be much less, as the unabated emission in the supply side through demand reduction is much lower than the total emission which is envisaged for or projected for 2050. In Working Group 3 report, the illustrative mitigation pathways include a set of transformative pathways that illustrates how choices may lead to distinctly different transformations that may keep temperature increase to below 2 degrees or 1.5 degrees Celsius. Also, what is important is that a stronger emphasis on demand-side mitigation implies less dependence on CDR and consequently reduced pressure on land and biodiversity. Model results show in low demand scenario, the different mitigation strategies could lead to phasing out of fossil fuel dependence and requirement for CDR in energy systems through this century. Now, many challenges such as dependence on CDR, pressure on land and biodiversity, and reliance on technologies with high upfront investment are significantly reduced in model pathways that assume using resource more efficiently, as we said, in the low demand scenarios or the scenarios where there is shift to global development towards sustainability. While direct air capture and bioenergy and CCS feature in varying degrees in all pathways, but not in low demand scenarios. However, achieving zero CO2 emission at present is technically impossible, but net zero targets have been set by many countries, which acknowledges that CDR is required to counterbalance those emissions that cannot be eliminated completely. So here it shows the sectoral GH emissions at the time of net zero CO2 emissions compared to model 2019 emissions in all different illustrated mitigation pathways. So there are some emissions which still remain, which are mostly in non-CO2 from all sectors. And so what it implies is that in this context, it is highly relevant whether a country aims for net zero CO2 or net zero GHG emissions, since the bulk of emission that cannot be eliminated and thus have to be counterbalanced by CDR, and which is non-CO2, including that from agriculture. So in order to realize the mitigation potential of net zero emission targets, scrutiny of use and risks of carbon dioxide removal and attention to equity, near-term action coupled with long-term intent setting and ongoing monitoring and review are of primary importance. So Working Group 3 report provides a detailed assessment of what we know and what we do not know of CDR. Some measures such as afforestation, reforestation, peatland and coastal restoration and improved forest management can enhance employment and local livelihoods when governed appropriately. Even if we are able to scale up proven CDR methods like afforestation and reforestation quickly and safely, still it would take some time before they were able to remove carbon at their full potential. So CDR only will help achieve net zero emission if used in addition to and not in place of deep emission curves in all sectors and regions. So to discuss how the Working Group 3 report addresses CDR and its governance, the report is clear that it is important to discuss this within the broader mitigation strategies and net zero goal and their timings. How to raise mitigation ambition in this decade is crucial by using all possible and known options. Large-scale deployment of CDR will face major sustainability and feasibility challenges. However, we should not forget that lower energy demand enables 40 to 70% emission reductions by 2050 with lower reliance on CDR methods. Although we know that some CDR will be unavoidable to counterbalance the hard to abate residual emissions. Thank you very much.
Good morning, good afternoon, and good evening. My name is Massa. I'm an associate professor at the Institute for Future Initiatives, the University of Tokyo. Today, I'm going to talk about how the IPCC Working Group 3 report has addressed SRM and its governance. So here's how the Working Group 3 report covered the solar radiation modification, or SRM, or sometimes referred to as solar geoengineering. Perhaps because of its controversial nature, there is no mention in the summary for policymakers, and there's only a short coverage of this topic in the technical summary, or TS. Basically, it says international cooperation is emerging, but inadequate. Still, there's a substantial coverage of SRM within the main text. In chapter 3, there's a substantial coverage of SRM and scenarios based on integrated assessment models. And in chapter 14, there's a cross-working group box on SRM. And it covers a number of topics such as the proposed solar radiation schemes, how the scenario, the relationship between scenarios and evaluation of SRM risks to human and natural systems, and potential for risk reduction, public perceptions of SRM, ethics, and finally, governance of research and deployment. Since this is also shows up in the Working Group 2 report, Chris Trissas covered this topic fairly broadly in the previous webinar by C2G. And chapter 14 also talks about international governance of SRM. So what is SRM? Solar radiation modification, or solar geoengineering. It refers to proposals to increase the reflection of sunlight back into space in order to counteract human-induced warming and some of its harmful impacts. It's a novel option to deal with climate change, and it would not address the root cause of climate change, the increasing concentration of CO2 and other greenhouse gases in the atmosphere, and also bring about novel risks. So it would not address ocean acidification because it doesn't reduce the concentration of CO2 in the atmosphere. But why we talk about SRM is it can provide some climate risk reduction. And one of the most important messages from this report is that SRM cannot be the main policy response to climate change, and is at best a supplement to achieving sustained net zero or net negative CO2 emission levels globally. So it can help, but it's not the main one. In the future, if emissions reductions in the CDR are considered or perceived as inefficient, SRM may be seen by some people as the only option left to achieve the 1.5 degree or 2 degrees target temperature goals. So that's why we are talking about it. We don't have to use it, and even in the best case, it would be a supplement. Please remember that. SRM is an umbrella term. It covers a number of different subcategories. So the most studied one, the option is stratospheric aerosol injection, or SAI. The idea is to inject reflected aerosol particles high up in the atmosphere, or a gas that then gets converted to aerosols. And these particles, small particles or aerosols, they reflect sunlight back to space. Sunlight can be reflected at different locations. So when it is reflected by marine clouds, it's called the marine cloud brightening. And if it's reflected at the surface of the oceans, it's ocean albedo change. Or you can make the surface more reflective, or maybe it could be rooftops, but the roofs, but the ground-based albedo modification is another category. The last one, cirrus cloud thinning. technically this is not SRM, but because it intervenes in the Earth radiation budget, it is often discussed along with other SRM options. SRM risks and its ability to reduce climate risks, all these depend on the way SRM is used, including scale, timing, and type, etc. There is no DSRM. When you hear something like SRM does that, does this, you need some caveats. So here's a diagram from the special report on global warming 1.5 degrees, published in 2018. And this is a small scale temporary deployment scenario. So let's say with substantial mitigation, we achieve this kind of temperature curve into the future. But unfortunately, the temperature would exceed the 1.5 degree threshold without SRM. So you could deploy SRM to cut off this shaded area. This is just one of many possible scenarios. You could, of course, deploy SRM on a large scale, and such a deployment scenario could bring about substantial SRM risks. And of course, we can choose not to use SRM at all. And that's the key point. There's no DSRM. It depends on our choice about how to use it and what kind of what kind of SRM are we going to use. The cross-working group box also covers public perception and ethics. The publics are largely unaware of SRM based on the previous research, based on the interviews and the surveys. The surveyed respondents tend to reject deployment for the foreseeable future, but they tend to conditionally, cautiously support the need for more research because they think it is better to understand its risks and benefits. Unfortunately, studies are biased toward the global north. There are a handful of studies that have looked at the perceptions in the global south and developing countries, but that's pretty small in terms of share. In terms of ethics, there is a concern about moral hazard. This is about, so if the publics get to know about SRM, they would have reduced incentives and the motivation for reduced emissions. But the empirical evidence is complicated and limited. There is also worry about the slippery slope. So once you start research or demonstration, then that could create a vested interest or dedicated community, and that could start basically the whole process of locking in the society into SRM, and we would eventually do a large-scale SRM deployment. But it's difficult to ascertain whether this would happen or not. Lastly, this is a point already said above, but there's a need to involve Global South and the vulnerable communities because discussion has been biased toward the Global North or developed countries. Chapter 14 also covers the SRM governance of research and deployment. There is no international law that directly governs SRM. There are relevant international treaties, such as the Convention on Biodiversity, and the London Convention and London Protocol on Marine Pollution, but they do not directly address SRM. So there needs to be some work to be done. Because the science on SRM is at an early stage, depending on the perspective, some flexibility would be useful to facilitate research. But we need some oversight, and too little restriction would be problematic. Conversely, if we restrict research too much, that would stifle potential innovation. So in other words, science and governance is expected to grow and evolve together. So co-evolution is the key theme. In terms of near-term priorities, there's some proposal to address. So here's a list of certain things that could be addressed. So the first is to guard against the potential risks and harm. The second is to enable appropriate research and the development of scientific knowledge. Third, to legitimize any future research or policymaking through public and expert engagement. And four, ensure the SRM is considered only as a supplement with a priority on mitigation. Thank you very much. I'm looking forward to the discussion.
And thanks very much, Massa, Joashri, and Glenn, our speakers, for those presentations. If you'd like to rejoin us on the screen now, and then we'll begin our Q&A session. We have about 25 minutes remaining of the webinar. So to our participant attendees, now's the chance to put questions to our speakers here who join us live. You can submit your questions using the Q&A button at the bottom of your screen. And don't be shy, no questions too stupid or too complicated. We have some of the best minds in the world here, so let's make use of them. And if some of this stuff was over your head, then of course you can go back to the IPCC reports themselves, which are going to be a fabulous evidence base for years to come on these topics. But also you can visit C2G2's website, where we've provided some briefings and summaries and infographics that help understand some of the issues that have been raised by our speakers here a little further. And that's at 3wc2g2.net. So whilst our participants, our audience are thinking of some interesting questions to put to our speakers, perhaps I might take this opportunity to jump in and pose a question to perhaps each of you in turn. So Glenn, in your presentation, you mentioned something that I think also was echoed by Joashri, which was that carbon dioxide removal only has a function if you're doing mitigation as well. Now, this might be a very basic concept, but could you just say a bit more about why that is? Because for some of our audience here, it may not be self-evident. Why is it? It's not either or. It only makes sense if you're doing mitigation as much as possible as well. Is that the case, or can you explain that a little bit more?
Yeah, so we can take it to, let's say, the first order. You know, the big picture, main effects. And the challenge is that it's a scale question. So we currently emit 40 billion tonnes of CO2 per year. If we magically developed a technology which sucked 40 billion tonnes per year out of the atmosphere and buried it somewhere, you know, shot it out to space or something, so it disappeared completely, then we could, you know, hypothetically probably keep emitting what we're doing and keep and just remove that carbon. But there's no way amongst all the technologies that we know that we could remotely remove the amount of emissions that we emit in a given year. And so emissions have to drop drastically. Let's say if you get emissions down from 40 billion tonnes today to about 5 billion tonnes, then maybe we could remove 5 billion tonnes per year across a suite of technologies. But that's still, I would say, at the high end. You know, if you get emissions from 40 billion tonnes down to 1 billion tonnes, and you only have to remove 1 billion tonnes, then that's still a big number, but much easier to do. So the more you get emissions down, the much easier it is to use removals. And if you think that removals, we can't remove more than 5 billion tonnes a year, and we keep emitting 40 billion tonnes a year, then you can do 40 minus 5, 35 billion tonnes a year. That would be our emissions with removals without emission reductions. So it's sort of the maths which shows you that you have to reduce emissions radically. And on top of that, some removals might help.
Got it. Thank you. Joashri, I don't know if you want to add to that. Otherwise, I might just have a quick follow-up for Glenn on this.
I can just add one example to say why we need to consider this. Say, for example, we usually say in case of air pollution, if it is really difficult. And the cost of reduction is also enormously high, and you cannot actually reduce all of it. So very little pollution can be cleaned up. Even in water pollution also can be cleaned up, maybe with known technology and with manageable cost. So similar is the question here. The more you emit, it becomes harder and harder to remove. In working group 1, actually, they have really shown that how it becomes harder and harder if you have more and more accumulated emission.
Okay, thank you, Jayashri. So we've had the first few questions coming in, so I'll hold my follow-up question for Glenn, and we'll go straight to first question from Marie-Valentine Florin, who says, with which CDR options do you see the major sustainability challenges that you briefly mentioned? For example, do you think that DACs could incur large risks? I don't know, Jayashri, did you want to pick this one up? Otherwise...
Okay, so basically it is important, that if you look into, I would really urge you all to look into the table 12.6, very specific table in the IPCC larger report, where I really find very interestingly, it says, it lists all the different methods for CDR, and what are the risks and impacts, and what are its co-benefits, its costs, where the technology advancement is. So it really gives a wholesome picture. So if I think of that, then I would say that basically, if you look at that, you will see that first thing is that not all technologies are developed up to a particular level where it can be deployed. So that is another major issue, right? So it's not that we cannot think of ocean fertilization immediately because that technology hasn't developed up to that level itself. And so if you look into the risk, every option has its risk, but some risks can be managed, and some of the risks which are really hard to manage. So even if you take afforestation and reforestation, you can imagine a forest fire and think of the risk of that. So so how you are looking at these risks, and so every technology has its challenges. And so it has to be really looked into carefully, that how we really look into that, the cost aspect, and also risks to society and to, permanency of the storage also, because it's really important how permanently you can store the carbon that you remove from the atmosphere. Otherwise, leakage will take out what you have removed.
Thank you for that.
Can I just add something
Glenn,
on there, just quickly directly on the direct air capture, because direct air capture is often seen as the savior of all these risks, because it can avoid potentially some of the risks. So the advantage of direct air capture is the facility itself has a very small footprint compared to, for example, afforestation or bioenergy with carbon capture and storage and so on. So it doesn't take up much land, but direct air capture requires an exceeding amount of energy. And so you do have a land footprint associated with that energy. And also, if we're, getting close to 100% renewables, there might be, some fierce competition over that last bit of energy as well. So it's not necessarily free. And the other thing is we don't know that we can get the costs down. So at the moment, direct air capture is exceedingly expensive. Maybe we can get the cost down to an acceptable level, or maybe we can't. So there's also that uncertainty that maybe we just can't get this technology, because carbon dioxide is, 400 parts per million in the atmosphere. That's not very concentrated. And so to, pluck out so many small atoms of the atmosphere is not easy. And so we don't necessarily have we'll be able to get that technology down to a sufficiently cheap level. So very important that direct air capture, whilst it deals with some risks, certainly doesn't deal with all risks.
Thanks for that addition, Glenn. And that pivots us quite nicely to our next question. So we've heard about some of the challenges that you raised, Jayashri, around permanence, and also that Glenn's just raised with regards to some of the sustainability challenges, and feasibility is another issue you mentioned as well, Jayashri. But what about the cost? All this costs, doesn't it? Who's going to pay for it? How's it going to be paid for? Now, perhaps this is more of a policy question, but are there any insights that have come out of the report or that you're aware of in how this might be paid for?
Yeah, after you, Jayashri. After you.
Go ahead.
No, so what I wanted to say is that you need to address this cost at par with how you deal the cost of mitigation also, right? So because anyway, you have to look at it from that point of view, although it has to be associated with a specific need for hard to abate emissions and when you apply these CDR. So if you look at that hard to abate emission part, say for example in industries or in say non-CO2 emission which are remaining and which could not be reduced at the net zero timing and given the net zero timing and goal. So in that case, it may be cheaper, but who pays for this cost? That would always be a bigger question. How do you meet this whole mitigation cost question, right? So, I mean, I don't think it has been answered in IPCC report because that's going to be more a political question. Because this can be seen as a political question that who bears the cost burden of mitigation, how you relate it to the historical emission, or do you put the burden on those who has not emitted it? So how do you see this mitigation, cumulative mitigation today, and when do you really remove the carbon? So I think this cost burden, who shares the burden, that's a more is a more different question. And I don't think IPCC answers that because it is more about discussing that how much it costs, what are the benefits, and that's the question.
Good, all clear. Either of you like to add to that, Glenn or Massa?
Yeah, I can sort of add in a little bit on the equity dimension too. You know, I was talking about the scale. The scale can be immense of this technology, and in some scenarios, about 10 to 20% of global GDP would be spent on technologies to remove carbon from the atmosphere. So it's not a marginal number. But just to put that in perspective, like today, I think you can even go to some companies and you can pay, I don't know, $500, $1,000 or whatever, and, you know, forgive your sins for all you've emitted in the past 12 months or something. And that might sound relatively cheap, right? So I can go continue my life and just pay, you know, $1,000 a year and the problem's fixed. So there's a few issues there. You know, not everyone has $1,000 a year to pay. So there's a huge equity issue. And this is not reducing emissions either. So this is continuing on your lifestyle and offsetting your emissions. So whilst that might help you when we've got carbon dioxide removal at a very small scale, if you want everyone in the world to be able to do that, so then you need to have this 40 billion tons carbon dioxide removal, which just doesn't work. And so there's a big equity issue here if you also go to scale and think about who's paying it. And so does the rich world get the first take of the first carbon dioxide removal? You know, the first of the 5 billion tons, does that go to the rich world, or does that go to, let's say, hard to mitigate sectors, getting the hard work done, offsetting fertilizer production for our food production, and so on and so forth? So there's a really important prioritization. And just to add one very important thing, which Jayashri went into, is that mitigation, you know, deploying renewables to replace coal, for example, is much, much, much cheaper than these technologies to remove carbon from the atmosphere. So that's also very important to remember.
Okay, thanks for that, Glenn, as well. Now Massa, go ahead.
Yeah, I'd like to add one point about the financial aspect, the cost aspect, because of the scale of the CDR expected in scenarios is very large. So if you implement just as suggested in models, you're gonna do a lot of financial transfers across regions. Some countries do a lot more CDR for other parts of the world, and because of the sheer size expected in models, if you multiply that with the carbon price, that's going to skyrocket, and that's whether we can design such a financial scheme is a very big question. So I think there's a huge governance issue. It's a pure money, but it's a huge challenge. We don't have that right now.
That's a very interesting point, Massa. Thanks for that addition. I think just the scale that's talked about here that's coming across from the report that might be needed in future is frankly mind-boggling. And as you've said, Joshua, as the scale increases, so do the risks and some of these around feasibility and around the impacts, conflict over land use, I think you mentioned, for example. Just to pivot now to our other topic here that we're covering on solar radiation modification, Massa, we have a question here from Klaus Radunsky, who says, does the risks that come from SRM change given the magnitude of cooling to be achieved? I think that's the question. So if we're trying to do more cooling with this theoretic technology, do the risks increase sort of at the same rate, or what does the report tell us about this?
Yes, and the risk does depend on both effectiveness of cooling and the risk from SRM depends on the magnitude of SRM, of course, and that's kind of similar to CDR. So planting trees doesn't cause much problem, and releasing a small a tiny bit of aerosol particles in the atmosphere, it doesn't contribute to much cooling, or it doesn't create much risks either. So I think the best example would be termination effect. So if you deploy SRM on a large scale, and if you stop it suddenly, you're going to unmask greenhouse warming, and you're going to have a lot of very rapid warming over the entire climate system. But that magnitude depends on the amount of cooling. So if you have let's say 2 degrees of cooling, then if you stop it, the SRM, then you have a sudden warming of 2 degrees, which is unbearable, I guess. But if you use it to just shave off the exceedance, like overshoot beyond 1.5 degrees by 0.1 degrees, even in the worst case scenario, the risk of termination is proportional to 0.1 degrees of cooling. So that's, I think this is just one example, and many of the risks are, I believe, they increase non-linearly. So if you use the SRM on a smaller scale, the risks can be contained. So I think this is just another way of saying that SRM cannot be the main option.
Thank you, Massa. I'm going to follow on now with another question from Marie-Valentine Florin, who asks about, well, perhaps some context here. I think in the report says, and I think, Massa, you've said this, there are many uncertainties and knowledge gaps around the risks that are faced from this theoretical technology or approach of SRM. And what would be your recommendations or recommendations that have come through in the report about next steps for reducing those knowledge gaps? What next needs to be learned in order to help understand this approach better? Keeping in mind, I think Marie-Valentine mentions that policymakers are not keen on investing in research or looking for governance arrangements. So in that context, what do you think might be next concrete steps for reducing those knowledge gaps?
Thank you for this excellent question. I think I need to take off my IPCC hat, because the IPCC is policy relevant, not policy prescriptive. But whether we should do research on SRM itself, this is a highly controversial topic, and there are some scholars fiercely arguing against any research on, maybe not any research, but research on SRM, and there are some scholars arguing for such research, and it's a very huge controversy. But one thing we can get, we can learn from the report itself is that debate so far has been concentrated in global north, so developed countries. So that's true for the public perceptions research, and that's also true. We can get this lesson from ethical analysis. So there's a concern about the power relationship between global north and the global south, but we should, I think, engage global south better to really understand, this is my opinion, but we need to have a global conversation about this, whether we should do research or not. And right now, a lot of things have been written in English, but very few reports came out on the in the United Nations, for instance, and so the IPCC report will be translated into official 6 United Nations languages, but there are very little information about SRM in like non-English settings. So I think we need to talk more about this more openly.
Very good, thanks, Massa. And just a plug for some of C2G's resources, which are impartial. They're available in different languages as well, and we have briefings on this report and the other report and this SRM components there. But this is a very interesting point, and I recall reading in the report, I think in the cross-working group box on SRM, that SRM research is dominated by the global north. And that probably has implications for governance, I would imagine, as I think Maria Valentina's question was getting to. So what implications does this have for research on these emerging technologies being dominated by global north and researchers? And I don't know, perhaps also this is a question for Joashri and Glenn as well with regards to CDR, perhaps too. But Massa, first from you, what implications does this have? I mean, does it really make a difference, or what can you tell us?
I think it does, and I think we need to incorporate like those viewpoints and the views from the global south, and I think basically a lot of damages will happen in global south, and the reason we talk about things like CDR and SRM is climate risk reduction. So what does it do to the people who these technologies are intended to help? We need to know that, and I think I forgot whether we covered this in the IPCC report itself, but the National Academy of the United States, basically they made a recommendation about sort of research, including the viewpoint from global south, and I think we need to have a more collaborative research. If research is perceived to be okay, I don't know whether it's okay or not, but if we have to do the research, we need to do the research itself in a very inclusive manner.
Okay, thanks. Joashri or Glenn? Joashri, go ahead. You'd like to come back.
So basically, I would say that this is common good or bad. So from that point of view, I mean, it is important how we have global cooperation in knowledge sharing and technology development, because also we need to keep in mind we are talking about very urgent immediate actions, right? So if we have to take immediate action, it cannot be the old model of technology transfer that you deploy, you learn in one country, and then it goes to other countries, so that a very 30, 40 years of learning that happens globally. That is not possible. If you look into energy efficiency, it has taken 30 to 40 years to become a global phenomenon, but that's something which we cannot afford, right? So now any technology development to address the climate change need to happen with international cooperation. And this is something which has come up in IPCC report, chapter 15, where we talk about the international cooperation a lot. And so without international cooperation, I don't think any acceleration in mitigation or removal or radiation management, if need arises, this thing can happen. So this is extremely important, how the global cooperation can build into the whole process, so that from the very beginning, there are inclusive research which happens, and so that the benefit also goes to everybody at the same time without any time lag.
Thank you for that important point, Jayashree. Glenn, did you want to weigh in on that at all? Or?
Yeah, I'll just come in with a slightly different, or a scenario angle, I should say, and thinking about where most of these scenarios come from and who's developing these scenarios, you know, that I was showing in my presentation. And the IPCC report is based on a synthesis of about 1,700 scenarios that were submitted to the database. But those scenarios come from different types of models. And the models submitting the most scenarios, so just having a quick look here, out of the top 10 models that were responsible for about 60% of the scenarios, all but one are from Europe or the US. And I think I'd have to check, I think all but two are from Europe. So you could argue that we're looking at a European perspective of the mitigation challenge, which is based around these scenarios. And these scenarios are generally globally cost-effective scenarios, which means, in short, that they don't include equity. So if the cheapest mitigation is in India, the mitigation happens in India regardless of historical responsibilities or per capita or whatever. So these two perspectives, I think, are quite important to putting the context in on carbon dioxide removal, that it's very much coming from a European US perspective and not including equity. That's not to say that if other researchers from other regions had the capacity to do a lot more scenarios, whether they'll necessarily be any different or whatever, but I'm sure we would start to see a range of different perspectives, capturing, you know, from what Jayashree was talking about with the demand side, different aspects of the problem, different ways of thinking about the problem, etc. And we might find, you know, new solutions to the problems that we're not looking at because we're just blinded by our own perspective. So we need a lot more diversity in this field, I think.
Thanks, Glenn. And on that note, I think we should finish. I'd like to, we've just gone over slightly, but just remains to say thanks to our three speakers for today for sharing your thoughts and helping us to understand the IPCC's Working Group 3 report in a little more detail. For those that want to find out more, obviously the IPCC website has everything you need in full detail, but on C2G's website also there's resources to help understand a little more detail, and you can scroll down from the homepage and click on the IPCC button there. And thanks for joining us, and join us next time for C2G Learn.